Okay. So what I want to do is take you through Unit 1.4's handout, which is more set stuff. And I'm going to take you through 2A. Now 2A says formally prove anything in the previous problem that's true. Um, and I'll just tell you 1A is true. Now the way that you should justify in number one is use some Venn diagrams and see if the shaded parts are the same or not. You have to figure out, do you look at the double shaded parts, or do you look at the triple shaded parts, or do you look at the parts that are just anything that's shaded? Does that count? So you have to use the unions and intersections to figure out how to interpret that. But for number two, I'm going to tell you 1A is true for sure. And so I just want to take you through one example formal proof, just so you see it. And then you can use that to help you prove anything else that's true here as well. Use the same sort of process. So it's a little tedious because it feels kind of repetitive in certain ways. And you'll see I'm going to fudge a little bit right at the end too, just to save some time. So in order to prove that A intersect B intersect C equals A intersect B intersect C, I need to really prove two things. Part one is I need to prove that the left side is a subset of the right side. And I'll bracket those guys so it's more clear what goes inside the other thing. And then second part, I need to prove that the right side is a subset of the left side. So I'm just going to reverse those and keep the subset symbol pointing the same way. Okay, so there we go. Now, the part I'm going to fudge is part two, because you can probably imagine it's going to be just like part one, but pretty much in reverse. So part one's the only part I'm going to emphasize. You guys can fill in part two if you want. So the way that I'm going to do this is you want to pick an element. So in part one, you want to pick an element that's in this set and then prove that because it's in that set, it also has to be in the set on the right. And since you're picking a general element, any element you want, if that element's in the first set and it has to be in the second set, then the first set has to be a subset of the second one. Okay, so the way I'm going to start, I'm going to say let X be an element of A intersect B and then intersect C outside the parentheses. Okay, so what does that mean? Well, that means that X is going to be in A intersect B, and if you wanted to, you could use that symbol too instead. X is in C. And if you wanted to do reasons, which is never a bad idea, that's just because of the pure definition of intersection. Okay, well, let's use the definition of intersection again. So that's going to be this one. X is in A, and I'll use the symbols here. So in fact, let me switch that one. And X is in B, and then outside here, X is also in C. So again, I'm just using definition of intersection. We're going to use that one a lot, actually. Okay, now, if you look at that theorem sheet that I gave you with all those tautologies, theorem 1J is a totally stupid looking one, but it comes in handy here. Because theorem 1J says that if you have ands like here and here, like we do, you can switch those parentheses. So you can move the parentheses to be around the B and the C instead. So this is the same thing as saying X is in A and X is in B and X is in C all together here, like that. So this is theorem 1J. Alright, well, now I got that. So now we can start working towards this thing up here again. We're practically there. So now I'm going to use the definition of intersection again. So X is in A and X is in B intersects C, since it's in both of them. That's definition of intersection. And now I can do it one more time. So X is in A intersect intersect C. Definition of intersection. Okay, now technically you should really have another little line here that says what you just did. So since x in A intersect, whoops, oh yeah, no, that's right, like this with the parentheses around the first two, implies that x has to be in A intersect and then the quantity B intersect C. We know that the first half there, the first set, A intersect B quantity intersect C, is a subset of the second one. It seems pretty redundant, I think, but you know, as long as you can follow the logic, it'll make the stuff that we do later easier to understand. That's the only reason that we're doing this to begin with, really. Now, the second one, the part 2, is going to be practically the same thing as part 1 in reverse. So I'm not going to fill that in right now. You guys can do that. If you can find a way to phrase it properly, you can do the double arrow thing to save yourself a little time in the future. But for the first one, you might as well just do the whole thing just to be pure about it. And then once you're done, so you're going to work out this whole thing. And then at the end, you're going to have, you know, we know that A intersect B intersect C is a subset of the first one that we originally had, like that. And then you need one more finishing line. So now you need to say, since A intersect B intersect C is a subset of the other one, and the reverse, the one on the right is the subset of the one on the left. Oops, wrong parentheses. So since we know both of those things, we can say that they're equal. Alright, and that's the end of our ridiculously detailed proof.